All right, today we're going to decode what might be the single most elegant sentence in all of physics. Seriously, it connects everything from the battery in your phone to the forces that, hold the entire universe together. So, how does one little sentence do all that? Let's find out.
So, let's kick things off with a little puzzle. Think about this. You've got the slow, controlled drain of your phone battery on one hand, and on the other you have the just violent, chaotic explosion of a lightning strike. I mean, they couldn't seem more different, right? Total opposites. But they share a secret, a deep, fundamental rule they both have to obey, no exception.
And that secret? It's the law of conservation of electric charge. Now, this is a rule that's so fundamental that, as we're about to see, it basically underpins almost everything we understand about electricity and magnetism. You can think of it as a simple, unbreakable promise that the universe makes about charge.
Okay, so in its most basic form, we call this global conservation. And honestly, the best way to think about it is like a cosmic accounting rule. It just says that if you could draw a big imaginary box around a part of the universe and seal it off, the total net charge inside that box, add up all the positives, subtract all the negatives, that number will stay exactly the same, forever.
So here's the absolute key takeaway. Charge isn't created or destroyed. It's just moved around. That's it. You can't just snap your fingers and make an electron appear out of thin air, and you can't make one just vanish into nothing. All you can do is shuffle it from one place to another. That is the entire game.
But this is where it gets really, really interesting. I mean, knowing the total amount of charge in a system is great, but is it the whole story? Think about it. If I told you there were 1 million people in a city, that doesn't really tell you much, does it? Are they all crammed into one stadium, or are they spread out evenly? See? We need a deeper, more precise rule. And that brings us to the huge difference between global and local conservation. Global just says the total number is fixed. Fine. But local conservation? Oh, it's way more powerful. It says that if the amount of charge right here changes, it's because charge physically flowed from somewhere else to here. We can actually track its movement, point by point, moment by moment. It's not magic, it's just physics. And this idea, this principle of local conservation, being able to account for every little bit of charge in every single location, that's the real bedrock. And physicists, being physicists, found a way to write this whole profound truth down in a single, incredibly compact and honestly perfect mathematical statement.
And this is it, the continuity equation. Yeah, I know, it might look a little intimidating with all those weird symbols, but I promise you, by the time we're done here, you're going to understand it as clearly as a sentence in a book, because that's exactly what it is. It's a sentence.
So to read this sentence, we just need to know the words, right? Let's meet the two main characters. First up, you've got rho. That's the Greek letter rho. It's just charge density. Think of it as how much charge is packed into a tiny little space. Then we have J, which is current density. That just tells us how that charge is moving, how it's flowing. The other symbols, they just describe how these two things change in time and space.
All right, let's look at that first piece. That dou/t thing, it's just a fancy way of asking a really simple question. Is the amount of charge at this exact spot changing right now? If the answer is yes, and the number is positive, it means charge is piling up. If it's negative, charge is draining away. Easy. It's the build-up part of our story.
Now for the second piece. That del.j, we call it the divergence of j. It asks a totally different question. Is there a net flow of charge out of this spot? So if more charge is flowing out than flowing in, this term is positive. If more is flowing in than out, it's negative. This is the flow part of our story.
And here's where the magic happens. The equation puts it all together, with that plus sign and the equals 0. It's just saying that these two ideas, the buildup and the flow, they have to balance each other out perfectly. So if charge is building up in one spot, it must be because there's a net inflow of charge to that spot. And if charge is draining away, well, there must be a net outflow. You cannot have one without the other. That's it. That's the whole law, written as a perfect, logical sentence.
Okay, so why is this one sentence so unbelievably important? Well, because it's basically the linchpin holding together our entire modern understanding of electricity and magnetism. You've probably heard of the 4 famous Maxwell's equations, right? The bedrock of the whole field. Well, it turns out they're only mathematically consistent. They only work if this continuity equation is also true. Without it, the whole beautiful theory just falls apart.
But we don't have to stay up in the clouds of high theory. Let's bring this right back down to earth, to something you've probably seen in a high school physics class. A simple electrical circuit with a nice, steady, unchanging current.
So let's see what our big, fancy equation says about this simple circuit. First off, in a steady circuit, by definition, charge isn't piling up anywhere. It's just flowing smoothly. That means our build-up term, the del rho by dt, is just zero. So our powerful equation suddenly gets way simpler. It just becomes del dot j equals 0. Which means the net outflow of current from any point is 0. And what does that mean in plain English? It means whatever current flows into a junction has to be exactly equal to the current that flows out. And hey, that's Kirchhoff's current law, a cornerstone of circuit design, and it's just a special case of this deeper, more fundamental principle. How cool is that?
You know, there's another really beautiful way to look at this. Physics often describes current density, J, as just being the charge density, rho, times how fast the charges are moving, their velocity, v. And when you write it that way, the continuity equation looks exactly like the equation that describes the flow of a fluid, like water moving through a pipe. It's just one of those amazing moments where you realize nature uses the same elegant patterns over and over again.
And the reach of this one simple idea is just staggering. I mean, it's not just for circuits or magnets. It is absolutely essential for understanding the physics of plasmas, for designing the semiconductors that power our computers. It even has a direct counterpart in quantum mechanics for describing how probabilities flow. It is a truly, truly universal principle.
So after all the experiments we've ever done, after pushing the boundaries of physics to their absolute limits, how many times have we ever seen this law get broken? The answer is 0. Not a single time. As far as we can tell, this is a completely unbreakable rule of our reality.
So we're left with this one beautiful, compact statement that governs every single spark, every circuit, every signal in the universe. It perfectly, elegantly captures the conservation of charge. Which kind of leaves us with one last big question, doesn't it? If this one simple rule has such profound consequences, what other unbreakable conservation laws, like the ones for energy or momentum, are out there, quietly shaping the very fabric of our reality?